Okay, where we left off in the last video was we were about to talk about viscosity in section 11.4. Um, so viscosity is actually a resistance to flowing in a fluid. Generally, viscosity is used in reference to liquids, but it can also refer to gases because gases are considered to be fluids also. Basically, anything that can flow is a fluid, and gases can flow, so they're fluids too. But usually, gases have so little resistance to flowing that it's usually not even worth talking about viscosity in relation to a gas. But in relation to liquids, there are actually quite a range of viscosities in liquids. Some liquids are very thin and pour and flow very easily, and some liquids are sort of thick and syrupy, and they don't pour or flow very easily. So just as an example, some liquids with relatively high viscosity would be things like motor oil. And motor oil, you want the viscosity generally to be fairly high, but not too high, because of course the motor oil has to flow through the pipes and the tubes within the engine so that it can get to the parts that need lubrication. But also viscosity has to do with the ability of the oil to cling to a surface once it's spread across the surface. And so a motor oil with high viscosity tends to leave a coating on metal surfaces inside the engine for a relatively long period of time, whereas oils with really low viscosity would flow really well through the the pipes and the tubes within the engine, but they would basically dissipate. They would flow off the metal parts really quickly. So something with a relatively high viscosity would be something like motor oil. A lubricant with a really low viscosity would be something like WD-40, where it's very thin. But when you spray something with WD-40, it's not very persistent. Over a period of time that's usually not very long, it sort of dissipates and goes away, and you often have to reapply it. Something else like molasses and pancake syrup. Other types of oils like vegetable oils, olive oil, corn oil, those sorts of things, they tend to have high viscosities. Liquids with moderate viscosities, well, the best known one is probably water. Water flows more easily than things like motor oil or molasses, but water still does have a fairly substantial viscosity to it, particularly compared to other liquids with relatively low viscosity. Things like gasoline, alcohols, acetone, things like that. In general, surface tension and viscosity tend to go together. So something with a high surface tension would have a high viscosity, and something with a low surface tension would generally have low viscosity. Water is kind of an exception because water has a relatively high surface tension, but only a moderate viscosity. But otherwise, the two qualities do tend to vary pretty much in the same way. The unit for viscosity, at least in the SI system, is known as the poise, P-O-I-S-E. Symbol capital P, and 1 poise equals 1 gram per centimeter second. And just to warn you ahead of time, I, for some reason, have an uncontrollable urge to pronounce this word the French way, which would be poise. So if I say poise in the near future, I really mean poise. Anyway, the viscosity of water at room temperature is about 1 centipoise. And since poise is an SI unit, you can use metric prefixes with it. So 1 centipoise would be 1/100th of a poise. And other substances like motor oil would have higher numbers associated with their viscosity. And other substances like, say, alcohol would have lower values associated with their viscosity. Generally speaking, stronger intermolecular forces lead to higher viscosity. And that's also true of surface tension too. Stronger intermolecular forces generally lead to higher surface tension. And that's why the two qualities tend to go together. They're generally going to be either both high or both low or both somewhere in between. But viscosity also depends on molecular shape. And that's because we're talking about things flowing. In order to flow, the molecules have to be able to slide over and past one another in the process of coming out of the container or traveling along a pipe or a tube or something like that. And the fact is that depending on the shape of the molecule, those molecules might tumble over each other very easily, but certain sizes and shapes of molecules might actually become literally physically entangled in each other, which would result in more difficulty in flowing and a higher value for viscosity. So generally, the viscosity would be higher for molecules that have long chains because of entanglement. And also some type of branching. Also longer chains longer chain molecules would tend to have more dispersion force attractions, which would tend to hold them together more tightly, especially if they're sort of linear chains where the molecules can get close to each other. Then they tend to be more resistant to slipping over and past one another. And also the entanglement. If they do manage to come apart and start slipping over and past one another, they can actually just sort of literally get tangled up in each other if they're long chain molecules. To some extent, branching, that is, we're basically talking about molecules that are made up of carbon and hydrogen here. And the chains, long chains would be made up of carbon-carbon bonds. And you can form long chains of carbon-carbon bonds. Also, these long chains can have branches coming off the sides of them that would also be carbon-carbon chains. Branching sometimes raises the viscosity and sometimes it lowers it. It really depends on how long the branches are and how frequent there are. Basically how many of them are there along the main chain of the molecule. So So I'll just say that branching can either raise or lower viscosity depending on various details. Also, temperature has an effect. Okay, so the effect of temperature, well, we probably know from experience with things like molasses or maple syrup or things like that, that generally things flow more easily when they're warmer and less easily when they're cold. If you take maple syrup directly out of the refrigerator and try to pour it immediately, you're going to have a hard time doing that because that stuff is practically solid. But when you warm it up a little bit, it's much easier to pour. And that is exactly what the effect of temperature is. It adds thermal energy to the molecules, which counteracts the intermolecular forces and allows the molecules to move relative to each other much more easily. So thermal energy can counteract intermolecular forces. So viscosity decreases as temperature increases. Okay, there's also the concept of capillary action. Capillary action is responsible for several effects that we observe in chemistry. There, I think, has been some stuff in some of the, or sorry, I think there has been some stuff in some of the labs that refer to the meniscus that you have to deal with when reading the volume of a liquid in something like a burette or a graduated cylinder. That is because of capillary action that meniscus exists. And we'll get to that in a moment. Capillary action first is defined as the ability of liquids to flow into narrow tubes even if it's against gravity. So basically even flowing upward. And the example the book gives is collecting a blood sample by basically jamming a narrow little glass tube into your finger, which is a very pleasant image to look at. So basically, though, is if you do that, and if the tube is the right diameter, you can create a little blood fountain of blood that's sort of like spurting out of your finger into the glass tube and out the top. And this is due to a combination of two forces. And these two forces are cohesive forces. Which have to do with the attraction between the particles in the liquid. That is, the attraction of the liquid particles for each other. And there's also what are known as adhesive forces. And that is the attraction of the liquid for the container. In most cases, it would be glass. Okay, so most cases we'd be talking about glass as the liquid surface of the walls of the container. The adhesive forces will cause the liquid to spread out over the surface of the glass. And there are a couple of possibilities here now. And one would be that the adhesive forces are stronger than the cohesive forces. And this is the situation that we usually encounter in the laboratory when we're dealing with water and glass. And what happens here is the liquid is drawn up into the tube. And the cohesive forces between the particles of the liquid will draw up other liquid molecules along with the ones that are directly attracted to the glass. Okay, so some of the water molecules will be basically directly attracted to the glass, and those are the ones that are right on the surface of the glass. But there are many, many other water molecules being drawn up into the tube also, which are not in direct contact with the glass. So the adhesive forces are responsible for the water molecules that are in direct contact with the glass being drawn up. But the other water molecules, the ones that are not in contact with the glass, are being drawn up by cohesive forces between them and the water molecules that are attracted or directly on the glass. So adhesive forces will draw the liquid up into the tube in a thin layer around the outside, but then that layer of liquid will have cohesive forces for other molecules which will come along with them. And so you end up with a fair amount of water going up into the tube. The liquid basically rises up into the tube until gravity balances out the capillary action. And the height that the liquid rises up depends on several factors. One of them being what is the liquid and what is the surface that it's climbing up made of, and also how thick is the tube, and things like that. And as it works out, you can actually achieve a greater height for a thinner tube, which really makes sense because in a thinner tube, the adhesive forces between the liquid and the tube will pull up a layer sort of around the outer edge of the tube. And for a thin tube, the cohesive forces between those molecules being pulled up by the adhesive forces, the cohesive forces between them and the other liquid molecules that have to be brought up would be less extensive because there are fewer molecules that need to be brought up by cohesive forces if the tube is really thin. So you've got a thin tube the molecules right around the edges of it are being brought up by adhesive forces, and then the ones in the middle there are being brought up by cohesive forces. And obviously, you don't need very much in the way of cohesive forces to bring up such a small number of molecules. If you have a bigger, fatter tube, well, again, the ones around the very outside edge are going to be brought up by adhesive forces. And in the middle here, you've got a big area. You've got a lot of molecules that have to be brought up by cohesive forces. And so it'll still happen, but it'll happen to a much lesser extent than it will in the narrower tube. Okay, the other possibility would be that the forces are the other way around. So if the adhesive forces are weaker than the cohesive forces, the liquid doesn't go up the tube. And in fact, it will actually drop to a level below the surrounding liquid. Let me put it like this. And an example of this would be mercury in glass. You stick a glass tube into a beaker of mercury, you'll notice that the mercury not only doesn't go up the tube, but the mercury within the tube will be at a lower level than the mercury that's outside the tube. Also, cohesive versus adhesive. Forces are responsible for the meniscus. Okay, for water, you have a concave meniscus. And that's what happens when the adhesive forces are, the adhesive forces are greater than the cohesive forces, because this is the example of water and glass. And so when you have adhesive forces greater than cohesive, you have a concave meniscus. And what that means is, as you're looking at the, whether it's a burette or a capillary tube or graduated cylinder, the surface of the water looks like this. It basically sags down in the middle because the water is strongly attracted to the glass and is trying to creep up the sides, and the weaker cohesive forces are trying to pull water molecules along with it up the middle, but because the cohesive forces are weaker, those molecules in the middle reach a lower height than the ones on the edges do. And so you end up with a concave meniscus. Mercury in glass, on the other hand, gives you a convex meniscus. And that would look something like this. And that's because in mercury, the mercury atoms are very strongly attracted to each other, but they're not very strongly attracted to the glass. So in this case, the cohesive forces trying to bring mercury atoms up the center of the tube are actually stronger than the adhesive forces trying to bring mercury atoms up along the edges of the tube. And so the middle actually goes higher than the edges do. And so that's a result of cohesive forces being greater than adhesive forces. Would be mercury. Okay, moving on now, we can get into some of the actual phase changes. Section 11.5 is about vaporization and vapor pressure. We've already mentioned vaporization. It's just a fancy word for boiling. So we're talking here about the transition from liquid to gas. And vaporization in scientific terms can be defined as the process of transforming a liquid into a gas by addition of thermal energy to overcome the intermolecular attractions. Whoops. Okay, so it's the process of transforming a liquid into a gas by addition of thermal energy to overcome intermolecular attractions. And remember, to turn a liquid into a gas, you essentially have to overcome all of the intermolecular attractions, because gases have effectively no intermolecular attractions at all. The process is like so. Molecules of liquid are in constant motion because of thermal energy. The motion is both vibrational and translational. And rotational when it comes right down to it. So not only can the molecules vibrate in place, but they can actually rotate in place also, and they can move from one place to another. So that's translational motion. And the higher the temperature, the higher the average kinetic energy of the molecules, the faster the motion. Okay, so the faster the motion. And it's also true that not all of the molecules at any given temperature have the same kinetic energy. There's actually a distribution of kinetic energies where the average, you notice we keep referring to average kinetic energy. That's because not all of the molecules have the same kinetic energy. Otherwise, we could just say kinetic energy. We say average kinetic energy because some molecules have more kinetic energy than others. Some have less kinetic energy than others. And so we figure out what the average is, and that's related to the temperature. But at any given temperature, no matter how high or how low, you're always going to have some molecules that have more kinetic energy than most of the others for whatever reason. And you're going to have other molecules that have less kinetic energy than most of the others for whatever reason. And so that's why we keep using average kinetic energy. So not all of the particles have the same kinetic energy at a given temperature. And that's why we have a kinetic energy distribution. And so it's true that at any given moment, a certain percentage of the molecules present at the surface will have enough kinetic energy to overcome the intermolecular attractions to their neighbors and go off into the gas phase. So I'll write that again. At any given moment, a certain percentage of the molecules present will have enough kinetic energy to break free of the intermolecular forces and basically enter the gas phase. And interesting thing is that the percentage of molecules that have enough energy to break free and become gas molecules, the only thing that really affects that percentage will be the temperature. So at any given temperature, say, I don't know, 10% at room temperature, maybe 10% of the molecules at the surface of a glass of water have enough energy to break free of the intermolecular attractions and go off into the gas phase. Well, as long as the temperature doesn't change and it remains at room temperature, it's always going to be 10% of the molecules that have enough energy to break free and go off into the gas phase. So you take your original glass of water with the original amount of water in it, and those 10% of the molecules that have enough energy to break free and go off into the gas phase, they evaporate. So they're gone. You might think, okay, the other 90% of the water is just going to stay there because those molecules don't have enough energy to go off into the gas phase. But you'd be wrong, because that percentage, as long as the temperature doesn't change, that percentage is always going to be 10%. If the first 10% of molecules with enough energy will, evaporate and go off into the gas phase, the next 10%, basically that energy is transferred to 10% of what's left. And so another 10% leaves, and then another 10% leaves. And of course, all of this happens over time. It doesn't happen as quickly as I'm saying it. But that's why a glass of water left out in a room will completely evaporate over time. It's because there's always a certain percentage of the molecules that have enough energy to go off into the gas phase. And there's really no way to stop that except to lower the temperature or put a lid on the glass, one or the other. Basically, if you put a lid on the glass and it's an airtight lid, you'll still get some of the water evaporating, but the water vapor will be trapped inside the glass. And once it gets to the point where the air inside the glass above the water contains as much water vapor as it possibly can at the given temperature, then the evaporation stops, because there's no place for the water molecules at the surface to go. They're basically trapped at that point. But if you take the lid off, then it starts evaporating again. Okay, where was I here? The exact percentage The exact percentage depends on the temperature. And like I said, that means that the percentage will remain constant if the temperature remains constant. And overall, this process is called vaporization or evaporation. Evaporation and vaporization are actually the same process, and they involve the same amount of energy. It's just that the connotation is that vaporization refers to when you cause the process to occur quickly by adding heat, whereas evaporation is the same process, but it occurs over a longer period of time due to the thermal energy that was already there, and you haven't added any extra, thermal energy. But the amount of energy that it takes to evaporate a glass of water is exactly the same amount of energy that it would take to boil away that glass of water on the stove. And it's just that that the amount of energy is being put in very gradually in the context of evaporation, and for boiling it away on the stove, it would be much quicker. So you have to put a lot of energy in all at once. Also, there's a distribution of kinetic energies for the molecules of vapor above the liquid surface. And some of those with less or lower kinetic energy might return to the liquid surface through condensation. So some of the slower moving water vapor particles might come close to the surface where they start experiencing intermolecular attractions, and they're not moving fast enough to sort of get by those, and they get sucked in. And now they're liquid again. So you end up with sort of a process going back and forth, evaporation, condensation, evaporation, condensation. And it may not seem that things are changing over time because both of those processes will be going on at the same time, and you'll have some molecules evaporating and you'll have some molecules condensing, and some condensing and some evaporating, and it's all going on at the same time. And since we can't see individual molecules, it appears that nothing is changing. Actually, we're well over 30 minutes now, so I'm going to stop and go on to the second segment, and we'll continue we'll pick up where we left.